In the last class, we have seen how to apply dynamic braking to a DC series motor. We have mentioned that although it is possible to apply dynamic braking in a DC series motor by reversing the field terminal and connecting a braking resistance at the terminal of the machine, the problem is as the machine speed goes down, the braking torque also reduces. This problem can be overcome using a chopper, and we will see through an example how it is done. For that, let us assume that a DC series motor, the following rating 220 volt, 70 ampere, motor, the combined resistance R A plus R A C equal to 0.12 ohm, and the at OCC at 600 rpm is given by the following data. Ten 64 20 40 ampere, this is the OCC at 600 rpm. Now, we want to brake this DC series motor using dynamic braking and a chopper. The chopper duty ratio changes from so what should be the value of RB, so that at IA equal to 70 ampere, the motor brake in the braking region, the motor speed is maximum motor speed is 800 rpm. For that, what should be the braking resistance RB? From the magnetization data, we find that for N equal to for IA equal to 80 and speed equal to 600, the back EMF is 210. Therefore, at IA equal to same 70 ampere and back EMF and speed equal to 800 rpm, we can find out the back EMF N equal to 800 rpm IA equal to 70 ampere. First, you have to find out what is E. The given data is N equal to 600, IA equal to 70 ampere, E equal to 202 volts. Therefore, E at 800 will be equal to 800 by 600 into 202 269.33 volts. So, in the regenerative braking we know that E equal to R A plus R A C plus delta R B so into I A R A plus R A C plus delta R B comes to 269.33 divided by 70 or delta R B equal to 3.73 ohm. Now, at maximum speed we will keep delta equal to at its maximum value. So, delta max R B equal to 3.73 ohm or delta max equal to 0.9. Therefore, R B equal to 3.73 divided by 0.9. This gives me 4.14 ohm. Now, suppose with this braking resistance, let us try to find out what is the maximum torque we can get with this chopper when the speed goes down to n equal to 87 rpm. Now, as the speed goes down, we also reduce the effective resistance, then at lower speed we will operate at delta equal to delta mean. So, the total delta mean R B will be the effective resistance plus R A plus R A C will be the braking resistance R. This will come to 0.534 ohm, as R A plus R A C is given as also E equal to R I A. So, if we plot from the given data at 600 rpm, we can plot the E versus I A at 87 rpm. And then also plot E equal to, this is has to be taken in the reverse direction because current has reversed, minus 0.534 I A. And find out the intersection point. turns out that the intersection point I A comes out to be approximately 50 ampere. So, at 50 ampere from the given data we have E equal to 184 volts at 600 rpm. So, K phi at I A equal to 15 ampere, K phi equal to 184 volts divided by 600, 2 pi into 600 by 60, this comes to 2.928. Therefore, T E equal to K phi I A equal to 146.4 Newton meter. So, we can still generate so much torque at a reduced speed of just 87 rpm. We can also apply regenerative braking, and let us see during regenerative braking what kind of torque we can expect. So, let us say this same machine is supplied from a Vt of 220 volts through a chopper. And chopper driven. So, what should be the motor speed when delta equal to 0.5 and braking torque equal to T rated. Now, at rated motor torque at T equal to T rated, whether it is motoring operation or braking operation, I A will be equal to I A rated. This is 70 ampere. So, what is E? Now, it is braking operation. So, E equal to delta V T plus I A into R A plus R A C, that is equal to 0.5 into 220 volts plus 70 into 0.12, this comes to 118.4 volts. From the magnetization characteristics, we know that at I A equal to 70 ampere and N equal to 600 rpm, E equal to 202 volts. So, if E is to be 118.4 volts at the same armature current, then the speed must be So, even at this speed a regenerative braking torque equal to the maximum rated motor torque can be produced using a chopper. Now, also let us try to find out what is the maximum motor speed. If I want that I A to be same 70 ampere and if delta max is equal to 0.95, what is the maximum motor speed? At 70 ampere, please note that you will still generate the rated braking torque, because the current is rated. So, what is E? E equal to delta max into V plus I A into R A plus R A C, 0.95 into 220 plus 70 into 0.12, this comes to 217.4 volts. Now, for I A equal to 70 ampere, N equal to 600 rpm, E equal to 202 volt, and I A equal to 70 ampere and E equal to 217.4 volts, then N should be equal to 217.4 by 202 into 600 equal to 645.7 rpm. So, we see that 645.7 rpm we have a armature current of 70 ampere, a duty cycle of 0.95, the motor produces rated braking torque. Also at 351 rpm we can reduce delta to 0.5 and still obtain rated regenerative braking torque. In fact, delta can be reduced further, then even at a lower speed equal amount of regenerative braking torque can be obtained by using a chopper. In fact, choppers can be used for speed control of DC series motor. We know for a DC series motor, the torque speed characteristics is given by in order to this torque speed characteristics, looks for a constant R A and V T, this looks like this. There are two ways to change this. One is to change the armature resistance. With increasing armature resistance, I can reduce the lower the torque speed characteristics. However, as we know this is involves a lot of loss in the additional armature resistance. Another more efficient method will be to control V T, and this V T can be controlled by using a chopper. So, if we feed the DC series motor from a chopper, and this S1 operates at a duty ratio of delta, then the terminal voltage here will be delta V t and the torque speed characteristics will be given by hence by changing delta this is increasing delta. So, let us see through a problem the quantitative effect. The same motor that we have been using. Now, let us try to find out if I set a delta equal to 0.65, then what should be the torque for n equal to 400 rpm. So, with delta equal to 0.65, delta V t equal to 0.65 into 220, and this should be equal to E plus I A R A plus R A C or 0.12 I A equal to 143 minus E So, we can find out where this intersection point will be. At n equal to 400 rpm, we are given the OCC at 600 rpm, this we can scale to 400 rpm, and on this we can plot IA. So, this is 143, this will be intersection point IA 1, this IA 1, this is 143 minus 0.12 IA, this gives IA approximately equal to 70 amperes, and also gives a E of 134.667 volts. Torque will be equal to E IA by omega, that is 134.667 into 70 rpm. Please remember this should be OCC at 400 rpm, not 600 rpm. Two pi into 400 by 60, this comes to 225 Newton meter. So, given the delta and speed, we can find out the torque, or if we given the delta or current, we can find out the speed. So, chopper control is an effective method of controlling the speed of a DC series motor efficiently. However, if we do not, this, it has to be remembered that this chopper which is connected to the machine terminal has to carry the whole machine current. So, the switches that are used in this chopper should be designed to withstand the full current of the machine. This makes the system of speed control somewhat expensive. There are other simpler method of controlling the speed of DC series motor, in which case we can see that we can also control the value of KKF in the equation of torque speed characteristics in order to control the speed of a DC series motor. There are several methods for doing this. One is called the field diverter control. In this, what we do is that the field is shunted by a variable diverter resistance R T. If this is R A C and the total current is I A, then there is current I D and I A C. So, once we place a diverter, by adjusting the value of R D, we can adjust the value of IAC, and IAC in this case will not be, is not equal to IA. We can also find out what will be the value of IAC. IAC equal to RD divided by RAC plus RD into IA. So, in which case the torque speed characteristics will also change, because E equal to K phi I A equal to K K F I A C I A. Now, we have I A C equal to R D divided by R A C plus R D into I A let us call it xdia. Therefore, E equal to k kf xd this is omega omega ia Vt equal to E plus now Ra plus Rd parallel Rac into Ia. So, Vt equal to now Rd parallel Rac equal to Rd Rac divided by Rd plus Rac, this is equal to xd Rd rather xd Rac. Therefore, Vt equal to the current speed characteristics now will be and the torque speed characteristics will be T e equal to k phi f I a equal to k k f x d I a square T e equal to we draw this torque speed characteristics, it will look somewhat like this is decreasing x t. That is, this amounts to weakening the series field. So, we know that for the same torque, if the field is weakened, the speed increases. There are another method on somewhat the same line is called the tapered field control, in which tapped field control, in which there are several taps there are several taps that are taken from the series field, and actually at any given moment the field can be connected to any one of those taps. Here also we are basically changing the field ampere turns and hence the field flux. Let us say the total number of series field terms is in AC, and between the present tap it is in AC dash. So, effective series current I AC equal to N AC dash divided by N AC into I A, that is sum K AC I A. So, the resistance also as will be somewhat assuming them to be proportional to N AC dash by N AC into R AC to K AC R AC. Hence, in this case also we will get similar torque speed characteristics as in the case of field diverter, where x d will now be replaced by R AC. A special case of this type of field control is called where the field winding is arranged in several sections and series parallel combination of these sections are used. For example, let us say that we have a DC series machine whose field winding has two sections of equal number of turns. Each in AC by 2. Now, these two field winding can also be connected in parallel like this. whereas in this case the total current flowing through each of them is I A, here it is I A by 2 and this is I A by 2, total current being same I A. Then 80 ampere turns of the series field winding with parallel connection is 80 with parallel connection will be equal to 2 times the 80 of individual winding, which is NAC by 2 into IA by 2. This is equal to half NAC IA, which is half of 80 with series connection. Also RAC dash will be RAC by 2 parallel RAC by 2 will be equal to 1/4 of RAC. So, KAC in this case if we assume linear field, then phi in series will be equal to KF IA, whereas phi with parallel connection will be equal to half KF IA, hence only 2 speed are possible. Here only 2 speeds are possible. So, let us try to solve the how a few problems showing how the speed control can be achieved. Let us take a DC series motor. The OCC is given by IA E 0 0 50 ampere 78 100 ampere, this is at 900 rpm. 150 volts, 150 ampere, 192 volts and 200 ampere, 220 volts. The RA equal to 0.035 ohm and RAC equal to 0.015 ohm. The supply voltage Vt equal to 220 volts. What should be the speed and torque of the motor if at IA equal to 200 ampere with full field. Let us first find this out. With field total RA plus RAC equal to 0.035 plus 0.015 equal to 0.05 ohm. EA equal to 220 minus 200 into 0.05 equal to 210 volts. So, with IA equal to 200 ampere, N equal to 900 RPM, we know E equal to 220 volts. Now, here same IA equal to 200 ampere, we got an E of 210 volts. So, N equal to 900 into 210 divided by 220, this comes to 859.1 RPM. So, what is T? EIA by omega. So, 210 into 200 divided by 2 pi into 859.1 by 60, this comes to 466.85 Newton meter. So, with full field at IA equal to 200 amperes, we got N equal to 859.1 RPM and TE equal to 466.85 Newton meter. Now, let us see how these values will change when the field turns are reduced to half. Then the resistance RAC dash will be equal to RAC by 2, that will be 0.015 by 2, 0.0075 ohm. So, total resistance R equal to RA plus RAC dash will be 0.035 plus 0.0075, this will be equal to 0.0425 ohm. So, when IA equal to 200 ampere, then EA will be 220 minus 200 into 0.0425 equal to 211.5 volts. Now, NAC dash equal to NAC by 2. So, effective field current effective full field current equal to IAC equal to 200 by 2 equal to 100 amperes. So, for 100 amperes we have the given data, we have seen that at IA equal to 100 amperes and N equal to 900 RPM, we have got E equal to 150 volts. Therefore, now if our we have same IA equal to 100 amperes and E equal to 211.5 volts. Therefore, N will be 900 into 211.5 divided by 150 equal to 1269 RPM. And torque will be E IA by omega, that is 211.5, but armature current is 200 ampere divided by 2 pi into 1269 by 60. This will come to 318.5 Newton meter. So, with half the series field winding, now we have N equal to 1269 RPM and TE equal to 318.5 Newton meter. Comparing with the previous result, we find that as the series field turn reduces, the speed increases from 859 to 1269 and the torque decreases from 466 to 318. This is the field weakening mode of operation of DC series motor. Thank you.